Welcome back to the Deep Dive. This is the show where, we really try to cut through the noise and deliver the essential, actionable knowledge that can empower you.
And today, we are definitely tackling a big one.
A really big one. It's a foundational engineering challenge that I think really dictates the future of the enterprise. We're moving beyond the kind of AI we've gotten used to.
Right. We're past static, retrieval-based AI. That's the smart search function, the stuff you're familiar with.
And we're moving into the realm of truly autonomous agentic systems.
This transition is a fundamental change in how businesses operate. I mean, we are no longer just talking about systems that fetch and synthesize data for you.
Not at all.
These new autonomous agents are capable of really complex, multi-step planning. They can use tools. They can execute entire workflows with a pretty significant degree of independence.
It's an exponential jump in capability, it really is. But with that power comes a critical engineering conflict.
A huge one.
And that conflict is really the heart of our deep dive today. On one side, you have the incredible power of large neural networks. They operate using probabilistic reasoning, which means their output has this inherent variance. There's a degree of beautiful but totally unpredictable chaos to it.
And on the other side, you have the enterprise.
Yeah.
And the enterprise demands certainty. It needs auditability, reproducibility, regulatory compliance.
All things that are purely deterministic. It's this clash, right? The deterministic requirements of business meeting the probabilistic nature of intelligence.
Exactly. And our mission today is to explore how engineers are, rigorously addressing this gap. We need to understand the whole suite of solutions.
Right.
We're talking rigorous runtime enforcement, deep formal verification methods, and some really novel architectural patterns that are being implemented.
And the goal, at the end of the day, is to make sure this newfound autonomy is treated as a controlled variable.
A controlled variable. That's the perfect way to put it. It's a governed feature that executes safely by design, not some unconstrained risk that could just expose the business to all sorts of liability.
Okay, so let's unpack this core issue, the determinism dilemma. If you're not, deep in the weeds of machine learning infrastructure, you might think, well, if I give the AI the same input and run the same model, shouldn't it produce the exact same result?
This seems logical.
A neural network is, after all, just a massive sequence of mathematical operations. But we know that absolute repeatability, even on that forward pass, is a constant battle in production. So why is it so elusive?
Because the production environment is just infinitely more complex than the theoretical math equation.
Yep.
While the core algorithms are, yes, technically deterministic, the moment you run these massive distributed models across a whole fleet of servers, you introduce something we call hidden entropy.
Hidden entropy. Okay.
And this hidden entropy is made up of all these minute system-level details that, when they add up, collectively derail any chance of perfect repeatability.
So what are those specific sources of entropy that we really need to worry about?
Well, they often live at the lowest levels of the computing stack. I mean, one of the major culprits is hardware-level thread ordering.
Okay.
When you run parallel processes on GPUs or, these specialized AI chips, the order in which those threads complete isn't guaranteed. And that slight variance in timing can cascade into different floating point precision results.
And you just mentioned floating point precision. That's another big one.
A huge one. If you execute the same model on two slightly different compute clusters, maybe one is using 16-bit precision and the other is using 32-bit, the rounding errors will compound significantly across billions of computations.
And then there's just the infrastructure itself.
Right. The dynamic nature of cloud-based serving infrastructure, which is constantly spinning up and down resources, introduces this instability that makes pinning down a repeatable state almost impossible.
So the core of the model might be deterministic, but the distributed execution environment is fundamentally non-deterministic. So engineers are essentially fighting to stabilize the entire stack just to get a baseline of reliability.
That's the fight.
So what are the starting technical fixes they have to implement?
Well, the foundational fixes are absolutely mandatory, but they're not sufficient on their own. You have to implement strict version control, making sure model weights and dependencies are pinned so that updates don't introduce surprise behavior.
Standard stuff.
Right. And then for forcing deterministic output, you set the model's temperature parameter, which controls randomness. You set that to 0. And you use fixed persistent seeds for any random number generators. That ensures that at least the initial state is reproducible.
Those seem like common sense fixes, but the sources we looked at really emphasize that they are often insufficient. So where do the subtler, more insidious influences creep into the agent's decision-making?
They sneak in through the very context the agent is given. Agent behavior is just exquisitely sensitive to the system state and the prompt engineering.
How so?
Okay, consider context retrieval. If an agent pulls three critical documents for reasoning, the precise ordering in which those paragraphs are fed into the prompt, let's say document A, then B, then C can lead to a drastically different output than if it read B, then C, then A.
Right, the order effect. The
Right.
model pays more attention to what it sees first.
Precisely. And beyond that, tiny changes in the system, prompt wording, or even seemingly innocuous user session metadata that an engineer might totally overlook can influence the final execution path the agent chooses.
And this sensitivity led to a really critical concept introduced in our sources, the stable triangle.
I love that framework.
Me too, because it moves beyond just fixing the model, right? It defines what stability actually means for enterprise AI.
It does. The stable triangle asserts that true, verifiable determinism requires locking down the relationship between three critical factors. First is the seed.
And that includes all the static settings, parameters, version pins.
All of that. Second is the system state. This is the dynamic context, the exact order of retrieved documents, the prompt wording, all that session metadata we talked about.
And third,
The resultant side effects. So the action taken or the output generated. If you can enforce consistency across those 3 points, run after run, then you've achieved the necessary system-level predictability, even if the internal reasoning itself is still probabilistic.
this tension, wanting the predictability of a machine but the adaptability of intelligence, it brings us to a crucial comparison of computing environments. We usually think of systems as either totally deterministic or purely stochastic.
Right, one or the other.
But this agentic system has to live in a new, kind of uncomfortable middle ground. Let's contrast those three approaches.
It's a really helpful way to categorize the engineering requirements. So traditional deterministic environments, they demand high predictability. They're inherently...
That's for financial transactions?
Exactly. They're built for use cases like financial transaction validation or compliance checking, where if you put the same dollar amount and the same account number in, the output must be identical. They're brittle. If the input is unexpected, they tend to crash or just fail rigidly.
And then on the complete other end of the spectrum, you have the stochastic environments. This is the pure generative AI we hear so much about.
Right. And they're characterized by low predictability, a high influence from randomness, and just outstanding adaptability. They thrive in ambiguity, which makes them perfect for creative generation, brainstorming, or discovery.
But you can't guarantee the output.
You can't.
Yeah.
Because they're optimized for novelty, you cannot guarantee consistency across runs, which makes them totally inappropriate for direct mission-critical execution.
And this is exactly why the hybrid agentic system is emerging as the enterprise standard. It's trying to get the best of both worlds.
It aims for a necessary balance, yeah. The agent's core function, its probabilistic reasoning, that's what gives it the intelligence to solve complex problems.
Yes. But the system enforces high predictability at the system level.
Right, by constraining that intelligence within these auditable, predictable workflows. The verification mechanism shifts from simple unit testing to things like formalized plan validation and, crucially, runtime gating.
So you get the adaptability, but within a structure that gives you a clear, defensible audit trail.
You get dynamic routing and intelligent fallbacks,
Yeah.
but within a predictable structure.
Exactly. So if the brain is probabilistic, how do architects build the skeleton to be deterministic? This is where that concept of deterministic scaffolding comes in.
It's the structural solution to the problem. Instead of allowing the agent just unfettered freedom to use any tool in any sequence it wants, you leverage its planning power, but you enforce a rigid order of execution.
Sequential orchestration.
Exactly. The workflow is explicitly structured so that each stage relies on a fixed, verified dependency chain.
And that fixed dependency chain is so key because it stops errors from cascading, right?
It absolutely does. It creates a transparent, auditable path. And this structure also allows you to deploy these specialized agents, small, highly constrained workers, each operating within very narrow, predictable parameters.
Which reduces the risk of cascading failures.
Dramatically. If a probabilistic decision leads to a failure in stage 2, you know precisely where it happened, and crucially, stage 3 hasn't even started spinning up its resources yet.
So you gain the high-level reasoning capability without sacrificing the ability to debug, audit, and, most importantly, roll back decisions.
You've got it.
Okay, so we've established that control over the execution flow is absolutely paramount. Now, let's look at the foundational architectural blueprints that engineers are using to build safety into these systems from the ground up. The sources draw a really sharp line between monolithic and modular design.
And this is a lesson we've learned from decades of software architecture. It's just now being applied to AI. The monolithic agent, one giant general-purpose brain, it might seem efficient at first, but it quickly suffers from something called instruction dilution.
Instruction dilution, what does that mean?
Well, if you hand it a complex, high-level goal, the clarity of its original instruction just gets muddied across a multi-step workflow. This makes it incredibly difficult to debug, to audit, and most importantly, to control in production.
And the modular approach is the counter-strategy to that.
It is. Modularity solves this by breaking down that complexity into specialized, constrained components. It creates a multi-agent system.
So each worker agent has a very narrow scope.
A narrow scope, a tight set of constraints, and specific permissions. That specialization ensures that if the agent responsible for financial checks misinterprets an instruction, it can't simultaneously execute a major infrastructure change.
So you get resilience. The failure of one component doesn't bring down the whole mission.
It's safety through controlled, specialized compartmentalization. That's the key.
This philosophy leads us directly into the fundamental safety mechanism for mission-critical applications. The supervisor pattern, which is implemented through hierarchical decomposition. It really sounds like the manager agent is the ultimate corporate governance body in this ecosystem.
It truly is the governance layer. Its role is absolutely non-negotiable in complex systems. It has three main tasks. First is task decomposition.
Okay.
It takes these ambiguous high-level requests like optimize Q3 spend, and it translates them into discrete, verifiable subtasks.
So like pull current expense reports, identify transactions over $5,000, draft recommendations for vendor renegotiation, things like that.
Exactly, breaking the ambiguity into actionable steps. Second, it delegates those tasks to specialized worker agents. The finance agent gets the report, the compliance agent checks the policies.
And third, and this seems like the most crucial part.
It is. Before any action is finalized or executed, the manager agent acts as a quality assurance checkpoint. It reviews outputs from all the workers for policy compliance, for correctness, and for adherence to the initial user goal.
So the worker agents are allowed to use their probabilistic reasoning to solve the subtasks, but the manager agent is responsible for enforcing the deterministic rules and the structural integrity of the entire operation.
That is the perfect summary. It resolves the problem of high-level ambiguity by imposing verifiable structure, and for maximum safety, especially when agents need to build on each other's context.
Like the compliance agent needing the output from the finance agent.
Right. You have to stick to that sequential orchestration, all managed by the supervisor.
One of the most inspired architectural innovations for boosting runtime safety that I came across is the integration of reflection and iterative refinement. In essence, you're forcing the agent to become its own internal auditor.
This pattern is increasingly considered non-negotiable for any high-stakes enterprise agent. Instead of just executing the first response it comes up with, the initial plan or output generated by the primary agent gets internally routed through a separate, dedicated critique agent.
Okay, so what are the specific criteria that the critique agent is using to scrutinize the plan? Is it just looking for simple errors?
It's looking for much more than just simple errors. Its evaluation criteria are multi-layered. It checks against predefined safety invariants, things that can never be true, like never delete a production database.
Right.
It checks business rules, like no spending over the $10,000 threshold without human approval. And it performs deep factual grounding against the context it was given.
And what about the reasoning itself?
That's a crucial part. It also evaluates the reasoning confidence. If the initial agent shows low internal confidence in a token sequence, the critique agent flags that as insufficient.
And if the critique fails, what happens next? Does it just stop?
No, it immediately triggers a refinement loop. The output and the critique are fed back to the primary agent, forcing it to iterate, to revise its plan, and to generate a new output that addresses all the critique's concerns.
So the loop continues until the solution meets the required execution threshold.
It does, whether that threshold is confidence, compliance, or correctness.
This fundamentally changes the priorities of the system, doesn't it? It forces a bias toward quality and safety, even at the expense of speed.
It's the necessary trade-off in the enterprise, that iterative refinement process. It catches subtle policy breaches and internal logical inconsistencies that pure statistical testing would just completely miss.
And for the listener, this is what builds trust. A system that shows this thoughtful, self-correcting behavior is seen not just as clever, but as genuinely reliable and responsible.
Absolutely.
Okay, shifting to infrastructure. We're seeing the architectural foundation itself shift toward what the sources are calling cognitive microservices. How does this model address the critical needs of memory management?
We're really adopting a microservice paradigm where agents are these discrete service-oriented units. Each agentic node is highly encapsulated and standardized.
So what are the components of one of these nodes?
It has an input layer for receiving tasks, a cognitive core, which is the LLM or reasoning engine, a memory layer often using vector or graph databases for context retrieval, and an actuator layer that links it to the outside world through validated APIs or message buses.
Encapsulation seems essential there, but what's the specific memory risk that this architecture is designed to mitigate?
The primary risk is often called memory drift or context poisoning.
Context poisoning.
Yeah. If an agent maintains too much persistent or generalized context loaded over many different tasks, it becomes susceptible to data leakage across sessions. Or its reasoning can become influenced by irrelevant, outdated, or even adversarial information.
It makes it hard to audit why the agent decided what it did if its active memory is just bloated with junk.
Exactly. So the mitigation strategy, just-in-time data loading.
Just in time. Okay.
Yeah. This is so critical for auditability and risk reduction. Agents are designed to maintain these lightweight identifiers, basically pointers for external resources, rather than holding the data itself.
So they only pull in what they need when they need it.
Exactly. They dynamically load only the specific necessary context required for the current task through validated tool calls. By limiting the data entering the reasoning window, you dramatically reduce data leakage risks, you keep the system focused, and you ensure that the audit trail clearly reflects which pieces of data informed which specific decision.
We've engineered a safe structure with modularity, and we've built in an internal auditor with reflection. But once that agent is live, running at machine speed and interacting with real-world APIs and databases, we need real-time infrastructure-level governance.
Why are traditional application layer guardrails just not enough for governing these autonomous agents?
Well, traditional guardrails, they rely on assumptions of static code execution. They're often blind to crucial runtime context.
What do you mean by that? They don't know the current system state, the agent's current confidence level, or precise time-sensitive constraints. An autonomous agent, if you give it broad permissions, might interpret a perfectly valid instruction in an unintended way that leads to an unsafe or unauthorized action, simply because it's trying to be creative in solving a problem.
The intent is complex.
The intent is complex, so the execution needs to be controlled externally.
That is the perfect segue into policy-based governance, shifting that enforcement down to the infrastructure layer. Tell us about this crucial policy engine and its role in the stack.
This is the execution choke point. The policy engine is implemented at the infrastructure level, and it's designed to intercept every single agent-to-tool interaction before that tool or API call can actually execute.
So it's a gatekeeper.
It's a transparent, non-bypassable gate between the agent's decision-making core and the target resource, like a database or an external banking API. The agent itself doesn't even need to know it's there. It's totally transparent governance.
The genius of this approach is how it anticipates what you call agentic creativity. What do you mean by that, and how does this model defeat it?
So traditional security models like role-based access control, or RBAC, they assume good faith. They assign static permissions. This agent can access this database.
Okay.
Agentic creativity, however, means a clever or malicious user could craft a sophisticated adversarial prompt that co-opts the agent, using its own legitimate tools into performing an unintended or harmful action.
Can you give an example?
Sure. Coercing a database maintenance agent to delete critical records by framing the request as a cleanup optimization. The agent, in its attempt to be helpful, misuses its own authorized tools.
I see.
The policy engine bypasses this by validating the action itself against a centralized manifest of allowed behaviors at the execution layer. It doesn't ask, does the agent have permission to access the database? It asks, does this specific action to delete command during peak hours comply with policy?
So it makes it impossible for even the most sophisticated prompt-based attack to succeed because the enforcement is outside the agent's cognitive control.
Precisely.
And to make this governance manageable, the policies need to be written in a language that is both intuitive for security teams and, sophisticated enough to handle enterprise complexity.
Yeah, the emphasis in the sources is on using a declarative, intuitive, if then policy language. This structure allows security engineers to define really sophisticated controls that dynamically respond to context.
So things like, if the transaction value exceeds $100,000, then mandate human approval.
Or, if the agent is attempting a deployment to the production cluster outside of 11 p.m. to 3 a.m. UTC, then automatically deny the action and alert the Security Operations Center.
If the source IP address is outside the corporate network, then restrict all database operations to read-only.
Exactly. This infrastructure layer enforcement creates an airtight perimeter that governs the agent's effect on the system, regardless of its internal probabilistic thought process.
As organizations adopt this framework, they really need a roadmap for increasing trust and complexity. This is addressed by aligning the level of autonomy with the necessary safety controls, using the concept of agency perimeters, often mapped out in a scoping matrix. We need to detail these 4 scopes because this is the progressive maturity path for the enterprise.
This matrix is essential for structured growth. You can't just jump straight to full autonomy. You have to ensure that the rigor of your safety controls scales proportionally with the agency you grant.
Okay, let's start at the bottom of the ladder, Scope 1.
Scope 1 is no agency. This is where most early systems start. The agent operates in fixed, read-only execution paths. It might retrieve information or synthesize reports, but it cannot initiate any external changes or actions.
And the security focus here is pretty basic.
It's fundamental protections.
Yeah.
Strict process isolation and input validation to prevent simple injection or data exfiltration. Think of these as predictable, highly constrained copilots.
Okay, moving up to where the agent can start making changes, Scope 2.
Scope 2 is prescribed agency. Now, the agent can execute changes, but it's entirely dependent on a critical human bottleneck. It requires explicit human approval for all outcomes before execution.
The agent proposes, the human disposes.
Exactly. And the security focus here shifts to securing that approval mechanism itself, using things like cryptographically signed decisions and multi-factor authentication to ensure the human consent is genuine and auditable.
Now we enter the high autonomy zone with Scope 3, supervised agency.
Scope 3 is supervised agency. Here, the agent has high autonomy after a human initiates the task. It's using dynamic tools and services to achieve a complex goal. This is where that policy engine we just talked about becomes absolutely paramount.
So the focus shifts to runtime controls.
The focus is on runtime constraint evaluation, automated kill switches that can halt operations in milliseconds if a policy is violated, and sophisticated identity delegation to ensure the agent's actions are traced back to the authorizing user.
And finally, the pinnacle of autonomy, Scope 4.
Scope 4 is full agency. This is the ultimate goal. Agents that are capable of self-initiated actions and continuous operation across mission-critical systems, making real-time decisions.
The safety demands there must be immense.
They are. It requires machine learning-based advanced anomaly detection, continuous agent identity attestation, constantly verifying the agent is who it says it is and hasn't been compromised, and dynamic access controls that check the agent's current intent against its authorized capabilities in real time.
That shift from static permissions to dynamic context-aware control models is just profound. It brings us to this analogy of treating agents as overprivileged interns. It's a great way to think about the risks.
It is the perfect framing. You have to treat agents as entities that are highly capable, incredibly fast, and yet fundamentally require strict supervision. The risk is that they operate at machine speed.
Right.
A mistake that might take a human hours to correct could take an agent milliseconds to execute across an entire system. Granting them broad static permissions is just far too dangerous.
So dynamic least privilege becomes the standard.
Precisely. Permissions have to be strictly scoped to the task at hand, reflecting a just-in-time, or JIT, access model. The agent only possesses elevated privileges for the exact duration of a specific defined transaction.
And when the task is done, those privileges vanish.
And furthermore, for accountability, every single action, every tool call, every decision must be irrevocably associated with the original user's identity who kicked off the workflow.
That creates an immutable event trail, the forensic data you need for any serious audit or regulatory inquiry.
It's non-negotiable.
Speaking of accountability and internal controls, we have to address segregation of duties, or SOD. That's a core enterprise governance principle. How do we translate that basic system of checks and balances into an automated agentic system?
This requires moving toward a team of teams architecture, enforcing OSD through specialized agents. No single autonomous entity can hold unilateral authority over a high-consequence action.
So give us an example of that.
Okay, consider a critical financial workflow. You would have one specialized agent focused only on preparing the transaction details. A completely separate compliance agent would then perform the mandatory regulatory checks. And finally, a third execution agent would handle the final transmission of funds.
So the entity that prepares the data cannot also validate it, and the entity that validates it cannot execute it without consensus.
It's the digital equivalent of requiring two people to turn keys to open a safe. This separation mandates dual authorization for sensitive operations. The system must require multi-step approvals, often involving a combination of human sign-off and a supervisory agent signing off.
So you get verification of both the compliance and the technical correctness before the final action is taken.
This layering of oversight is the only way to effectively mitigate complex financial and regulatory risks at machine speed.
As agents start executing these complex, multi-step workflows across diverse enterprise environments, think multiple databases, external APIs, cloud services, we immediately run into this immense challenge of distributed transaction integrity. The source material highlights the painful risk of system inconsistency when these workflows fail midway. Let's use an example to clarify this risk.
Okay, let's imagine a highly critical multi-stage process like an agent fulfilling a major new client contract. Step 1, update the client status in the CRM system. Step 2, allocate necessary server resources using the infrastructure API. Step 3, initiate billing through the financial ledger system.
Okay, I see where this is going.
If the agent successfully executes steps 1 and 2, but then a network outage or a server crash occurs before step 3 can be logged in the financial ledger, the enterprise is left in this split brain or inconsistent state.
You've allocated resources, you've updated the CRM, but the client hasn't been charged, or the internal records just don't match.
Precisely. This partial outcome is a compliance and financial nightmare. To prevent this, architects have to borrow from decades of distributed systems principles, primarily the two-phase commit, or 2PC protocol.
So how does 2PC, managed by the agent controller, enforce atomicity, that all-or-nothing guarantee, in a workflow that's spanning multiple systems?
2PC ensures strong consistency. It guarantees that a distributed transaction either completes successfully across all participants, or it fails entirely, leaving no system partially updated. And it's executed in 2 distinct phases, coordinated by the agent controller.
Okay, walk us through phase 1, prepare.
In the prepare phase, the coordinator agent sends a request to all the involved participant nodes, the CRM, the infrastructure API, the financial ledger. Each participant has to locally validate the request for correctness and, critically, lock the necessary resources.
To make sure no other system can modify them.
Right. They don't commit the changes yet, they just stage them and then they vote, responding to the coordinator with either a yes, meaning they're ready to commit, or no, they can't commit.
And then phase 2, commit.
The coordinator waits for all the votes. If it receives unanimous yes votes from all participants, it sends the universal instruction to finalize the transaction. All staged changes are committed simultaneously.
And if even one says no?
If even one participant votes no, or if any service fails to respond within a timeout period, the coordinator instructs all nodes to immediately roll back any staged changes. This absolute guarantee of rolling back is what preserves the strong consistency of the entire system.
That sounds extremely rigorous, but the source material correctly flags the critical caveat with 2PC, the risk of blocking.
This is the Achilles heel of 2PC for sure. If the coordinator node itself fails during the protocol, especially after the prepare phase but before the commit phase is finalized, the resources locked by the participants might just remain locked indefinitely.
So those services become blocked.
They become blocked, unable to respond to other requests, which leads to system degradation and resource exhaustion until someone can manually intervene to resolve the state.
So for systems that need extremely high availability or where you can tolerate slightly delayed consistency, 2PC is just too risky. And that's where the Saga pattern provides a crucial alternative.
The Saga pattern is the modern, more flexible alternative, and it's particularly useful when you're integrating many different, possibly heterogeneous services. Instead of one massive all-or-nothing transaction requiring locks, a Saga is defined as a sequence of local transactions.
So each local transaction updates the system state, and then what?
It publishes an event that triggers the next local transaction in the chain.
And what's the mechanism if a failure occurs halfway through that sequence? How does it roll back?
This is the core innovation, the compensating transaction. Each local transaction in the saga has a corresponding compensating transaction designed specifically to undo the changes made by its partner.
Oh.
If the sequence reaches transaction N and N fails, the system automatically executes the compensating transaction for N1, then N2, and so on, working backward to roll back the entire workflow.
So if the flight booking fails, the preceding hotel reservation is immediately canceled.
Exactly. This avoids system-wide locks, it mitigates the blocking risk of 2PC, and it ensures the system achieves eventual consistency.
It might take a moment to fully clean up after a failure, but the integrity of the data will eventually be restored.
It's about balancing the need for robust recovery with the operational need for high availability and throughput.
Beyond just maintaining transactional integrity, we have to ensure these complex agentic workflows can survive system failures like server crashes. We need durability and execution. So how do we ensure these long-running tasks don't just get lost?
This is the principle of durable execution building crash-proof workflows, which is absolutely vital for production reliability. Durable execution platforms treat the agent's complex plan not just as code, but as a long-running stateful process that can be mapped into immutable traces.
Like a persistent flight recorder.
That's a great analogy. And the core mechanism enabling this is systematic checkpointing. The agent's entire state, its current progress, its reasoning history, all its internal variables, is checkpointed in a persistent external database after every significant step or decision.
So if the agent is interrupted during a complex task, say a server crashes during a multi-day compliance review,
the durable execution engine automatically recovers and resumes the workflow from the last recorded checkpoint. The agent doesn't need to rerun finished actions, which guarantees fault tolerance and continuity for asynchronous, complex background operations in the enterprise environment.
We've covered the structure and the runtime governance, but now we arrive at the highest bar for safety, mathematical proof. The sources make a really compelling case that traditional software testing, where you just check for exact output matches, is fundamentally inadequate for agents because their reasoning is probabilistic. We need formal verification.
That's right. Traditional testing can only confirm functionality on known paths and known inputs. Formal verification is a completely different discipline. It uses mathematical techniques to prove that the system meets its specified requirements for correctness and safety, regardless of the agent's internal probabilistic nature.
You're replacing empirical trust with mathematical certainty.
That's the goal.
So let's explore the two primary formal logic techniques being applied, starting with model checking.
Model checking is essentially an exhaustive search of the system's control logic. It systematically explores all possible states and transitions that an agent's decision-making flow could possibly take.
And the purpose is to guarantee that critical safety invariants are never violated.
Exactly. These are rules that can never be broken, and you check them across the entire state space.
Could you give us a detailed example of a safety invariant that would be tested using this method?
Absolutely. Think about an autonomous infrastructure agent that's managing server fleet deployment. A key safety invariant might be: the system must never concurrently deploy conflicting configuration versions.
Okay.
Model checking, often using a language like temporal logic, allows us to formally express and prove this. The formula might be structured as: it is globally true, G, that if the agent attempts to deploy configuration X, it is finally true, F, the configuration Y is not running.
And if the control logic contains any path that violates that formula?
The model checker identifies it immediately, demonstrating a fundamental design flaw before it ever gets to production.
That moves verification from a trial and error process to a preventative mathematical discipline. And the second technique is theorem proving.
Theorem proving is even more rigorous. Instead of just exploring states, it involves constructing a formal, mathematical proof that the agent's design adheres precisely to its specification.
And this is used for the highest stakes applications, right, where even rare errors are catastrophic.
Exactly. Think financial risk modeling or highly constrained medical diagnostic systems.
Why is this method superior for those critical decisions?
Because it demands logical consistency from the ground up. Theorem proving allows developers to generate mathematical evidence that the agent's core reasoning aligns with all regulatory guidelines or clinical protocols or financial rules.
So you're literally proving the system is right, not just that it hasn't failed yet.
That's the difference. You're proving correctness.
So formal verification addresses the design, but once the agent is running live, especially when it's interacting with complex human factors, we need to monitor its behavior in real time. This is the domain of runtime verification.
Right. Runtime verification continuously monitors the live execution stream against dynamic properties. This is particularly challenging in human-agent interaction, where the agent's internal state, its goals, its intentions, can shift rapidly based on user input.
And to manage this, architects are using something called belief graphs.
Belief graphs, yeah.
Help us visualize this. What exactly are they tracking in real time?
A belief graph models the dynamic evolution of an agent's internal state. So, its beliefs about the world, its current goals, and its immediate intentions, as it progresses through an interaction. You can think of it as giving the agent a highly structured, constantly updating internal diary of its own thought process.
So by tracking that evolution, you can verify that its influence stays within ethical and safety boundaries.
You get a framework for it, yes. It facilitates counterfactual reasoning during the interaction itself.
So the system can analyze what-if scenarios dynamically.
Precisely. By integrating these graphs into formal logic systems, you gain a mathematical tool for analyzing complex agent strategies and preventing potentially harmful operational outcomes that might arise from a subtle misalignment between the agent's intention and its executed action.
That handles the internal consistency, but the performance of an agent isn't static. It degrades over time due to external context shifts. This slow degradation is the insidious problem of stochastic drift detection, and specifically, agentic drift.
Agentic drift is a major production hazard. It's this slow, quiet deviation in performance or reasoning path that occurs as the underlying business conditions change, or as the model learns unintended shortcuts that optimize for speed over safety or compliance.
Right. Unlike traditional software, which stays static until you update it, agents subtly evolve their behavior. So you need continuous, intelligent assessment.
It's mandatory.
To catch this slow deviation in the high-dimensional output space of a complex agent, we need something far beyond simple threshold alarms. The sources detail a very sophisticated solution. Adaptive Multidimensional Monitoring, or AMDM. What are the core components of this framework?
AMDM is built to handle multiple heterogeneous operational metrics, things like cost, latency, decision quality, compliance failure rate, all at the same time. It uses a three-phase approach to detect when the agent's behavior has statistically left its healthy operating zone.
Okay, phase one, metric normalization.
This is critical because, you can't compare dollars to seconds directly. So we use rolling z-scores for all metrics. This calculates how many standard deviations the current reading is from the rolling mean of the last X hours or days.
And using a rolling mean accounts for natural trends, like latency being higher on Mondays.
Exactly. It allows for a fair, aggregated comparison across all the different dimensions.
Phase two, adaptive thresholding.
Instead of using fixed thresholds that just generate constant false positives, AMDM uses exponentially weighted moving averages, EWMA, to compute adaptive thresholds for each normalized axis. The EWMA places greater weight on recent data, allowing the thresholds to intelligently adapt to expected environmental fluctuations.
So the system ignores temporary spikes from server load, but still flags genuine pathological degradation.
Right. And then the final, most sophisticated step, the one that really catches complex drift, is Jane anomaly detection.
This is where we bring in the Mahalanobis distance.
The Mahalanobis distance. It sounds highly technical, but it's simply the statistical equivalent of measuring how far off course our agent's multidimensional output is, taking into account the natural shape and correlation of all its metrics.
So it's not just checking if one metric crossed a rigid line.
Not at all. It calculates the distance of the current metric vector, all those normalized scores aggregated together, from the centroid of the established healthy operating distribution.
So it detects if the agent's overall style of operation has changed, even if individual metrics haven't spiked drastically.
Exactly. If that distance exceeds a critical value, it signals a statistically significant deviation in the agent's behavior pattern. It allows for rapid detection of safety violations or goal drift with far fewer false positives than if you monitored each metric on its own. It catches a subtle systemic change that simple rules would completely miss.
Before we move to the wrap-up, we need to make sure we clearly differentiate the types of drift we've been discussing and their specific mitigation strategies.
This clarity is crucial for maintenance, absolutely. So, concept drift occurs when the relationship between input variables and target outcomes changes. The underlying business goal or reality has shifted. Mitigation there requires automated retraining and manual policy adjustments.
Okay.
Data drift is when the distribution of the input data itself changes. New user demographics, new payment methods. This requires continuous data observability and feature engineering updates.
And label drift.
Label drift relates to changes in the meaning or value of classifications. This often requires integrated human feedback loops and an adjustment of the agent's internal value system.
And finally, agentic drift itself.
And agentic drift, that deviation from the internal reasoning blueprint, is mitigated by intent-driven testing and continuous validation of the intermediate reasoning steps themselves, often using those belief graphs we just talked about.
This deep dive has comprehensively demonstrated that verifiable autonomy is not some secondary feature. It is a rigorous, demanding engineering discipline. To succeed, the enterprise has to achieve this convergence across so many areas.
Architectural modularity, continuous reflection via critique agents, ironclad infrastructure layer policy enforcement.
Adherence to distributed consistency protocols like two-phase commit and Saga.
And ultimately, mathematical proof using formal verification and AMDM.
The path that organizations must follow is clearly laid out in the agentic maturity model. It really provides a progressive roadmap.
It does. It starts with the crawl stage of simple rule-based co-pilots. Then it progresses through walk, where you get semi-autonomous coordination.
Then to run, which is autonomous orchestration with full monitoring.
And finally to scale, which is establishing these self-learning ecosystems with continuous identity checks and advanced anomaly detection. This is a systemic, multi-year shift from merely assisting human users to actually running mission-critical business functions autonomously.
And central to this maturity path is the demand for quantitative safety. We have to move past these vague assurances and demand measurable metrics for trust.
Absolutely. Enterprises must track quantitative targets that relate directly to business outcomes and risk. Decision quality is a primary one. You should be targeting completion rates well above 90% for production tasks.
But the real measure of trust is the safety and security metric.
That's the one. It must target an extremely low adversarial success rate, ideally under 5%. Tracking metrics like resource utilization is important, sure, but these core decision quality and security metrics are the currency of regulatory compliance and organizational trust.
And finally, the ultimate safety layer, the final circuit breaker against catastrophic error, is confidence-gated reasoning.
This is the agent's self-awareness mechanism. It uses internal model signals like token probabilities, entropy, and internal consistency scores to quantify its own belief or certainty in its output and its plan.
So intermediate and final outputs are strictly gated based on this contextual integrity score.
They have to be.
So if the agent says, I am 95% certain this is the correct action, it proceeds. But if it says, I am only 51% certain, the system has to react.
Precisely. That low confidence rating must trigger a severity-based response. A minor deviation might just trigger a notification or mandate a human review.
But a critical low confidence violation,
Like trying to access a restricted API with a high entropy score, that must trigger an immediate suspension of agent operations. It has to halt the process entirely to prevent cascading errors across the environment. This capacity for self-correction and self-suspension is essential for risk management in high-speed autonomous operations.
So what does this profound engineering shift ultimately mean for the enterprise? We aren't just deploying software, we are building systems that are provably safe enough to be, well, digital colleagues.
That is the necessary conclusion. The move to the agentic enterprise is not just a technical change in how we process and move data, it is fundamentally a reimagining of the relationship between identity, authority, and control within the business structure.
We're establishing a highly controlled, auditable, paved road for innovation.
A road that is powerful, but most importantly, demonstrably and provably safe for the high-stakes world of business.
And as we consider these digital employees, capable of self-initiating, executing, and auditing complex multi-step transactions, all tied to an immutable event trail based on their verifiable permissions, the question for you, the listener, to mull over is this. If the system of record can prove exactly what a fully autonomous agent did and why it did it, what does the verifiable identity of an autonomous digital employee mean for the future delegation of human responsibility and accountability in the workplace?
A fascinating line of inquiry. The engineering is there, but the operational implications are just beginning. Thank you for diving deep with us today.
We'll catch you next time on The Deep Dive.